Hello, everyone. You are welcome to clip 1 in this part 8. So in this part, we are going to explore some emerging technologies in wireless communication and also some applications. So let us start in this part of introduction to cognitive radios and networks, and also unmanned aerial vehicles. So what is cognitive radios? Actually, as we have already seen that most of the spectrum is occupied already or licensed. So it is not possible that just you come and start submitting or transmitting in the spectrum. So the process is very long and also very costly. So of course, there are free bands or unlicensed band like at very high frequencies, for example, above 60 gigahertz, but those bands are not that good in coverage area, or the propagation behavior of electromagnetic wave at those frequencies are not that good. So how could we start new services, or how could we start new systems in telecommunication systems in the frequencies less than 3 gigahertz? So the idea came that most of the spectrum less than 3 gigahertz, they found that we have a lot of spectrum holes. There is what is known as a spectrum underutilization. So we have underutilization for the spectrum less than 3 gigahertz, as you can see, for example, in this figure. So if you allow me just to change. Yes. So you can see already that, for example, in these frequencies, we have the utilization, most of the frequencies less than 25%. Those measurements were done in 6 different areas in US, and this is the average result. So since we have such free or holes in the band, why we don't recycle them, use them, even they are used or licensed to other users? But as far as we guarantee that there is no harmful interference to the others, then it would be possible that to use these bands. So the cognitive radios that offers a novel way of solving the spectrum underutilization problem. Okay, so but one very important condition, that we shouldn't make any harmful interference to the primary user. The primary user is the user which the band is licensed for them. So we can define the spectrum hole as here, that the spectrum hole is a band of frequencies assigned to a primary user, but at particular time or at a specific geographic location, the band is not being utilized by that user. So if the band is not used at that location, or the primary user doesn't have receivers in that area, so we can, under some conditions, as we will see them later soon, that we can utilize our transceivers in that area. I just give example. If you have a radar system and there's some frequencies assigned for this radar, but in certain area there is no radar, let's say within a few kilometers, that then why we don't use that band in that area? So the cognitive radio transmitter must adapt all its radio resources, like transmitting power, data rate, transmission time, carrier frequency, bandwidth, beamforming, all of them, they must be assigned in the way that we don't make any harmful interference to the primary user of that spectrum. You can see here that I gave this simple example, that we have TV broadcasting, for example, and then we have TVs in the area of that transmitter, and in some areas that we check if it is possible that we use the same band of this TV for transmitting and reception in that area by cognitive radio. So for example, we can use the same band to transmit data rate, for example, for internet application or for the Internet of Things, IoT, and so on. But it is like critical that there shouldn't be any harmful interference. So we shouldn't have any interference for the TVs, for example. Because of that, it is important for the receivers actually in that sense to check the spectrum. So it is very important to check the spectrum, that there is no we check the interference level. And you can see here that we have what is known as sensing collaboration. So maybe we have like collaboration between different receivers of the cognitive radio. CR here means cognitive radio receivers or secondary receivers. They can sense the spectrum in this area, and they can exchange information about the interference level in that area. So then we can and we can send also this information, the spectrum sensing, as well as the channel state information to the transmitter of that secondary users. And then the transmitters, they can decide if they should transmit, or they should stop, or they should just reduce the power, and so on. So the main condition is to protect the primary user. Who is the primary user here? Is those TVs actually. Those TVs are the spectrum, the primary users for this channel. Okay, so it is very important here that we can achieve some communication between the cognitive radio receivers and their transmitters, and in the same time protecting the primary user from being like corrupted, or the signal is highly interference. So why we call this as cognitive? Actually, cognition, that human have cognitive capability because it is based on the sensing. So we can sense the world around us, for example, with our eyes or like ears and so on. So we can sense the environment, and then we process the sensed data for learning, memorization, awareness, and reasoning. So in this cognitive radius, because they have the sensors, so if they can sense the spectrum around it, and based on this sensing of the spectrum, it means that the interference level or the signal level in that spectrum, that based on that, they can take decision, or they can take a reasonable decision in order to protect the primary users, as well as to maximize the utilization of that available holes or available, like white space or the gray space in the spectrum. Because we have sensing, and based on the sensing, we can make like intelligent action. We call this system as cognitive radius. So we have sensors for the spectrum. Based on the sensors, we can also build some like learning algorithm that we can have some like learning about the statistical behaviors of the people or of the systems using, or primary users using that spectrum. So the cognitive radius, actually, as I said, that they should like have list of primary tasks, like protecting the primary users, and maximizing the utilization of the available channel, where the secondary users collaborate with each other in order to get more information about the distribution of the interference in that geographical area, and also learn the statistical variations of behavior of the RF signals, or the behavior of the primary user when they send, when they don't send, and so on. So we have actually 3 necessary tasks for cognitive radius communication: radio sense analysis, that estimation of the interference temperature of the radio environment localized around the user's receiver. So you can see that the user receiver, or the secondary receiver, is the critical item here. Detection of spectrum holes. All the time we are scanning the spectrum, and we try to find any holes. If we find holes in the spectrum, then we try to utilize that holes. predictive modeling of the environment. So those are the first task, that's radio sense analysis. The second task is based on channel identification, based on the received signal from the secondary transmitter. Then we can estimate the channel parameters, and based on these parameters, we can adjust the transmission or the communication parameters in order to maximize the utilization of the available spectrum hosts. And this could be done, of course, through the dynamic spectrum management. Actually, there's one critical point here, that once we have a single like secondary transmitter and single secondary receiver, then in that case, we can be almost sure that if there is no, we don't make harmful interference to the primary receiver, everything will be fine. But the problem that we might have many like secondary users for the channel. So in that case, because secondary users actually they are not licensed to use the channel, they are allowed to use the channel or to use that band. It is allowed to use at the condition that don't make any harmful interference to the primary users. And if we have many of them, then the accumulated interference, we have accumulation of the signals like in the transmission. This might cause that serious interference to the primary user. So how can we protect the primary user? Actually, we have like two ways. The first one is by using like a database registry. So for example, if we have TV channel, they broadcast within certain like band, but we know that this TV channel is working, let's say from 6 at morning up to, let's say 12 at night. So this information is like used. This information is used by the cognitive radio, so they know that they don't use the channel within that time because it will be like occupied by the primary user. After, above that time or after outside that time, then it is free to use without limitation. So this is one option, using the database registry. But of course, this one, if the time has been changing, so we need all the time to update the secondary users with this information, and it will need also high infrastructure costs. And also the secondary users, keep this in mind, that the secondary users or the secondary transceivers, they should be as simple as possible. It can be like IoT, like Internet of Things, or it can be like some sensors and so on. So it is not that good solution that to have this database registry in every item there. The second way is to use information broadcasting. So maybe we ask the primary users to send beacon signals all the time, but also this will need like positioning to be known by the secondary users, and also it will need high infrastructure costs, because when you send like beacon signals to indicate, for example, if there's interference or if or about the existence of the primary users, then we need the secondary receivers also to have the capability to detect this signal and demodel this signal, and this will increase the complexity of the system. The second solution is by using that spectrum sensing. So this looks to be the most straightforward way that we can just sense the spectrum, if the spectrum is free or not. Okay, and mainly it should be sensed by the receivers, but of course even the transmitters, they can sense around them that they will not make any interference to the closed like receivers of the primary user. Okay, so the secondary transmitter, they should sense also, and the secondary receiver, they should sense as well. Okay, and we have two types of sensing. It can occupancy or occupancy sensing, which means that we just sense if there is like RF signal in the spectrum. Okay, we don't care from this RF signal came, but if there's RF signal, then we just sense that. And the second way, which is more effective, but it needs more cost as well and a little bit more complicated, is by using identity sensing. So the identity sensing that we try to see from where this RF signal came, because this RF signal could be also from other secondary users that we don't care for, because secondary users, they can compete each other to use the resources, the available resources. But if this like spectrum or this RF signal is of the primary user, then we should stop. So we need to identify that RF signal. Okay, so this occupancy sensing is by, as I said, just detecting the spectrum. And of course, we have a lot of challenges with occupancy sensing as well, because there's the estimation of the spectrum is one of the complicated things, actually, because of like known as like spectrum leakage and so on. It cannot be like very, very accurate. Okay, so all the time we might have that probability of fault detection. So the topic is very interesting and very wide as well. But now let us just touch this cognitive radio topic. So maybe I need just to, yes, to comment this slide as well. So you can see here, for example, if we have the secondary user, so the secondary user, they sense or they estimate the power or the energy in certain band. So this is a band of interest. Okay, and then they found that band that there is interference already, or there is RF level, which is given by the green here. But we know that this primary user receiver, they can manage well until this red line. So we shouldn't like cross this red line. Okay. So in that case, we have this gap actually. This gap, it means that our secondary system or secondary radio system, they can transmit over this band, but at the condition that they don't cross this red line. So we have actually opportunity here to use the channel. We have opportunity to use the channel in that sense. And finally, in this topic, we see just the spectrum sensing algorithm. So we have that identity-based or feature-based detection. We have matched filter-based sensing. Matched filter is nothing but just you have like some of the physical layer of the primary user in your secondary user, secondary receiver. So they demodulate the signal and then they match if there is like to be sure that if there is a primary user signal in that area or not. But of course, this one is very costly compared with the others. And then we have the cyclostationary feature detection. The cyclostationary feature detection, actually, we don't detect the whole signal, but we are detecting, for example, some general part of the signal. For example, if there is a broadcasting primary user where they use, let's say, 3 gigahertz frequency, then this frequency, they should be like modulated over cosine wave, as we know before. So in this cyclostationary feature detection, they detect if there is cosine wave, if there is some signal is not natural, it's not noise, it's not just noise. So if there is some, because cosine wave, it has some like repetition pattern, okay? So or periodic pattern. So if there is a periodicity in the signal, then we can have like we have some algorithms that we can detect if there is cyclostationary signals in the area. Okay, so this is easier and simpler to implement than using the whole matched filter technique. And then we have the energy-based detection. So we just detect the energy of the RF signal. So we have the time domain sensing, we have frequency domain sensing, we have wavelet-based sensing, and multi-taper spectral estimation. So we have different techniques of the energy-based detection. Energy-based detection is easier to implement, but it is less effective than the feature-based detection. So in conclusion, just to conclude that cognitive radius is one proposal that to handle the problem of underutilization of frequencies less than 3 gigahertz. For example, if we have an area where there is like 700 gigahertz, which was not very well utilized, then actually it will be like big benefit for us, because we can transmit signals like internet, for example, information, or we can use it for IoT, and it can be used for many different applications. The propagation behavior at 700 megahertz is very good. The signal could be the coverage area can be very wide, and also we have enough like bandwidth that we can also transmit or receive very high data rate. This is the idea of the cognitive radius, utilizing the underutilization or underutilized spectrum at a main condition that don't make any harmful interference with the primary user of the channel. Protect the primary user of the channel. If you can transmit and receive over it is licensed band, do that, but don't make harmful interference. So this is the conclusion of the cognitive radius. Okay, now I will talk a little bit also about wireless communication with UAV or with drones. So the idea here is how to use this unmanned aerial vehicles networks. So this UAV or drones has been proposed recently to be part of the wireless networking, either with cellular or satellite, IoT, smart grids, and so on. So why? UAV are relatively very cheap to operate, comparing with like launching low Earth orbit satellites, for example. And they are many opportunistic to operate UAV, and these are that utilized very well, but also we have a lot of challenges with UAV. So you can see here, for example, we have this drones. So the drones could be used to, for example, to be as a relay between the base station. If we don't have base station in certain area, that the like ambulance car or some critical use vehicle, that they can communicate with the infrastructure of the communication. So drones can do that, can like provide vehicle to anything communication to protect the to increase safety, and it can work also in smart grid, so it can collect data from sensors there, or from it can also have measurements of the weather there. And actually we have too many applications. Can be also connected through the satellites as well, over for example new satellites. Okay, so what are the benefits of using UAV or drones? As we said that drones are usually low altitude, which means that they can provide very good line of sight channels, and this channel can be excellent. So we have like a very high data rate over that channels. It is cost-effective solution, fast and flexible deployment. Because of the mobility actually of the drones, then their antennas could be like oriented in order to maximize the signal to noise ratio, so we get the best communication performance. Okay, and they have actually some very important and critical applications, or at least proposed applications for using UAVs. What happens if we have like outage area due to disaster? For example, we have like earthquake, so we lost all our base stations. How could we cover the area? So for example, using of course we have this satellite communication, but also in the satellite usually we use special kinds of handsets. So you cannot use your mobile phone GSM or directly over the satellite. So you need to have their own like special handsets. But here we can actually have drones with small base stations, especially this the radio part. Okay, in 5G, as we discussed before, in the 5G, we can have what is known as virtualization. So we can separate the part. So we can have some of the radio part to be over the drone in that case. So we have here, you can see that we have drones that can provide the wireless communication, cellular communication over that area. And then they can, we can have multi-hubs or relaying of the information up to the core network or to the, maybe we have some base station far away from that area. It can be also used, they can be used for collecting data. For example, we have thousands of sensors just or IoT deployed in a remote area where we don't have any base station or any collecting of data. Then we can just submit our or send our like UAVs, so they can go through over that area and collecting data, and the data could be like just saved in the drone, or it can be in online transmitted to our like backbone system or core network. Also, it can provide communication if we have like natural shadowing, like big shadowing, like mountains, for example. We can use a couple of them to provide as a link between two different base stations, for example. However, that UAVs have like critical challenges as well. The first thing, of course, safety, that we need all the time to control the UAV. Of course, the UAV can be also integrated with AI, like a driver with artificial intelligence to avoid crashes, but still they need that to have our own control over them. So usually they have a channel, is called like control and non-payload communications, that we need to be connected to the UAVs. Also, because UAV, usually they have line of sight channel. So it means that we cannot use MIMO. MIMO as a concept of spatial multiplexing, they are working well in reach of multipath channel. But when we have just line of sight channel, so it is not that useful. Also, using beamforming, sometimes because of the fast movement of the UAV, it cannot be that effective. So we have some technical problems, but the major or the most important challenge in the UAV is that it is weight and it is size. So it is limited actually. So we have very limited size there. And because of that, we have also limited battery. And the battery is used, part of the battery is used to like, to give energy for the rotors of the drone to fly, but also it will be used for the, for example, for the base station or for the RF part in the communication. Because of that, we need very like accurate and very effective utilization of the power, so to keep the drone flight as much as possible, or as long as possible. So in that sense, we need to have very like effective and efficient algorithms for using the RF part if we want to integrate these drones with small base station, or at least the RF part, the radio part of the base station. So you can see, for example, here that we have the drones, and then we can have the control center. This is the control signal that we can control the flight of the drones, and then we have this data link connection with the drones, and also we can have secondary the control link with the drones in case that this one was disconnected. So we should have, we will be able to control the drones over like LEO satellite or CubeSat, as we will describe next. Okay, So that's all about this part. So this clip one. Now we talked about the concept of cognitive radio and the concept of the drones networking and communication. So in next clip, we talk about CubeSat. Thank you very much, and we meet in the next clip. Thanks.